We're back in part 2 here, and we're going to cover some more definitions, some more rules, and we're going to start with independent and dependent events. Remember to take notes, pause often, complete the you try problems and the examples with me and on your own. When we talk about events that are independent, basically it means that they don't affect each other, and events that are dependent are related to each other. And so if we think about that, we did conditional probability. A given B is still going to be A because it doesn't matter what B is because they're independent. And B given A is just probability of B because it doesn't matter what happens with A. So independent means that it doesn't really matter what happens given the other one. So looking at this one here, and again, if we kind of go back here, if we want to know are two events independent, we can check these formulas out and see if they're true. So are A and B independent events? So let's take a look. If they were independent, then the probability of A given B would be equal to the probability of A because it wouldn't matter what happens with B. So when I look at that, I can see that 0.45 does not equal 0.65. So are these independent? No. Are they mutually exclusive? So if two events are mutually exclusive, if we kind of go back here, that means that their intersection is 0. That, remember, mutually exclusive A and B, they're completely separate. There's no overlap, so their intersection would be 0. So are these 0? Well, we know the given, right? We know this conditional, so let's use that formula to help us. We know that this is equal to this right here. That's the formula. So now we've got that the conditional probability is 0.45 is equal to, we don't know this, but we want to know this. We want to know if this is 0, right? And over the probability of B here, which is 0.30. So we would multiply both sides by 0.30, and we've actually done this before. We get that the intersection is actually 0.135. Well, that's not 0, right? So these are not mutually exclusive. So what is the probability that neither A nor B takes place? So what they want to know is that the probability of A or B, but not the complement, right? Not A nor B. So when we're trying to figure this out, we would say, okay, well, that's the complement of 1 minus the probability of A or B. So we can figure this out here. A or B is the probability of A plus the probability of B minus the probability of A and B. Whew. So that's 1 minus 0.65 plus 0.30 plus, and we figured this one out, the intersection here was 0.135. Make sure you add all these up first and then subtract. So we're going to do 1 minus all that, and we get 0.185. That is the probability. So suppose that for a given year, there's a 2% chance that your desktop computer will crash and a 6% chance that your laptop computer will crash. Moreover, there is a 0.12% chance that both will crash. Is the reliability of the two computers independent? So let's go back to the definition. If they're independent, then the conditional probability won't change anything. So we want to figure out, basically here, if the two conditional probabilities work out here. So let's take a peek. So the probability of your desktop crashing is 0.02. The probability of your laptop crashing is 0.06. And the probability of both, the intersection here, is 0.0012. Now be careful there. It's already 0.12. So you move it over twice. All right, so now we want to know, all right, what's the probability of the desktop crashing given your laptop crashed? So that's our intersection there over the probability of the laptop crashing. So 0.0012 over 0.06. When we type that into the calculator, we get 0.02. And remember, if they're independent, it won't matter given the laptop. It would equal the probability of the desktop, and that does work. Let's try the other way. Laptop given your desktop. They both crash. Oops. This would be given that the desktop crashed and the desktop there. When we divide those out, we get 0.06, which is equal to the laptop. So they are they independent? Yes. And it makes sense. If your desktop crashes, it probably has nothing to do with your laptop, most likely. So they are independent. All right, so we're going to talk about the multiplication rule here. We're going to do two different instances, and that's the last thing we'll cover in these videos of this topic. So multiplication rule of both. So when we're talking about the multiplication rule here, if we know the intersection, here is another way. And if we think about it, this is actually just the previous one. So if we know the conditional probability, we know the intersection over this. What this is just saying is, hey, multiply both sides here. It's the same thing. So this is just a variation of something we've already done before. So a stockbroker claims from the past that the probability a client owns stocks is 0.6 and that a client owns bonds is 0.5. The probability that they own both, if she already owns, so given they own stocks, is 0.55. What is the probability that they own both? So what do we have here? We have the probability of stocks is 0.6, the probability of bonds is 0.5, and we have the probability of bonds given that they own stocks is 0.55. And we want to know that they own both. So let's see here. We've got the probability of bonds and stocks. Let's just write out that formula. That's the intersection. That's the both here. That's what we want over the stocks. So we can fill in the blanks. We know that the probability here is 0.55. We're looking for this. And the probability of stocks is there. So we'll multiply both sides by 0.6. And we end up getting 0.33. So 33% chance. Given that the client owns the bond. So now they're giving you the given first, which is a little confusing. What is the probability the client owns stocks? So this is the given. It's given they own bonds. Given they own bonds. See that? They gave it to you backwards. What is the probability that the client owns stocks? So this is the probability of both over this. So we know the probability of both is 0.33 and the probability of a bond is 0.5. So we would find that that is 0.06. Go ahead and give this one a try. Press play when you're ready to see the solution. There you go. So now when we're dealing with independent events, things that are independent, when we're looking for the intersection, we can actually just multiply the product of the probabilities. So the probability of passing this exam is 0.5 for John and 0.8 for Linda. The prospect of John passing is completely unrelated, independent, to Linda's. What is the probability that both Linda and John pass the exam? So the probability for John is 0.8 and the probability for Linda, this is 0.5 and this is 0.8. So the probability that John and Linda both pass, because they're independent, we can just multiply them. And so we get 0.5 times 0.8, we get 0.4. What is the probability that at least one of them passes? Well, at least one would be John or Linda. So that's the probability of John plus the probability of Linda minus both of them passing. So that's 0.5 plus 0.8 minus, and we got that previous answer before, 0.4, and so that's going to be 0.9. Go ahead and give this one a try and press play when you're ready to see the solution. Actually, there's two here, sorry. And there you go, and that concludes this section.